In this video, we are looking at Chapter 8, Lesson 4, which is the significance of experimental results. So suppose you flipped a coin 20 times. Even if the coin were fair, you would not necessarily get exactly 10 heads and 10 tails. But what if you got 15 heads and 5 tails, or 20 heads and no tails? You might start to think that the coin was not a fair coin after all. So hypothesis testing is used to determine whether the difference in two groups is likely to be caused by chance. For example, when tossing a coin 20 times, 11 heads and 9 tails is likely to occur if the coin is fair. But if you tossed 19 heads and 1 tail, you could say it was not likely to be a fair coin. To understand why, calculate the number of possible ways each result could happen. There are 220 possible sequences of flips. Of these, how many fit the description 19 heads, 1 tails? And how many fit the description 11 heads and 9 tails? So down below, it calculated it for us. Since there are 167,960 possible over 20, 8,398 times as many sequences that fit the latter description as the first. The result, 11 heads, 9 tails, is 8,398 times as likely as the result of 19 heads and 1 tails. Therefore, it is very likely that a coin that flipped 19 heads and only 1 tails was a fair coin. However, that outcome, while likely, is still possible. Hypothesis testing cannot prove that the coin is unfair. It is still possible for a coin to come up with 19 heads by chance. It is just very unlikely. Therefore, you can only say how likely or unlikely a coin is to be biased. So before we look at example 1, I just want to remind you that the word null means 0. So the null hypothesis is that the difference between the two groups is 0. So now looking at example 1, a researcher is testing whether a certain medication for raising glucose levels is more effective at higher doses. In a random trial, fasting glucose levels of 5 patients being treated at a normal dose, which is group A, and 5 patients being treated at a high dose, which is group B, were recorded. The glucose levels in mmol or over liters are shown below. So A, state the null hypothesis for the experiment. So the glucose levels of the drug will be the same for the control group A and the treatment group B. And then B, compare the results for the control group and the treatment group. Do you think that the researcher has enough evidence to reject the null hypothesis? So the minimum, maximum, median, and quartile values are shown in the diagram. There is a small difference in the two groups that is likely to be caused by chance. If anything, the treatment group actually shows a tendency towards higher glucose levels. The researcher cannot reject the null hypothesis, which means that the medication is probably just as effective at the normal dose as it is at the high dose. And it's really helpful to draw a box plot for this, just so you can see the differences between the two groups. Okay, and then the last example. A tax preparer claims an average refund of $3,000. In a random sample of 40 clients, the average refund was $2,600 and the standard deviation was $300. Is there enough evidence to reject his claim? So first off, you want to calculate the z-value. So you would do 2,600 minus 3,000, divide that by 300 over the square root of 40. So in this, the 2,600 is your average refund. The 3,000 is the average refund that your tax preparer claims. The 300 was your standard deviation, and the 40 was your number of clients. So doing this, you would get negative 400 over approximately 47.43, which is negative 8.43. So the z value is negative 8.43, and your absolute value of your z value would be 8.43. And since that is greater than 1.96, there is enough evidence to reject the claim of the tax preparer.